Okay, so in our next example, we bring back in this completing the square idea that we talked about in 8.1. All right, if we have x squared plus 2dx plus d squared, we can factor as x plus d. So what we usually end up having to do here is to compute what we need to add to complete the square. Since the formula is 2dx, we always have to take half of the x term, right, and then square it, and then it'll factor as x plus or minus, depending on whether that's negative, that number, quantity squared. So we did a few examples with completing the square previously. In this example here, and we also saw a second example when we eventually had to work with the arc sine. Those techniques that we had to do there with arc sine, try to get it to fit the arc sine derivative, those are no longer necessary now that we have our trig substitution. So again, the stuff we had to do here to try to get this thing to fit the inverse tangent stuff, all those manipulations, will actually have easier time on those problems now. But we still have ones where we will have to complete the square. And that's what our upcoming example deals with here. So consider the following problem here. The integral of dx over x squared minus 6x plus 34. Okay, so on the surface here, there's really just nothing to do. All right, there's just nothing that I can do as far as any kind of substitution. If I try to let u be the bottom, I need 2x minus 6. I don't have that. So what we do is we complete the square. What we do is we go through this completing the square process. So we go through this process of completing the square. So what we do is we group our x's together. You have a little bit of space there. Plus 34. And so we go through our process, which again, remember, involves taking half of the x term. Of course, first off, the x squared has to have a 1 in front of it. So we take half of that number, call it b, or I'm calling it b in this example, or d, or whatever you want to call it. Half of that number should be negative 3, and then we square it. Should be 9. So to complete the square, I need to have a plus 9 on the inside. So I do that, x squared minus 6x plus 9. And then I account for that by undoing it on the outside. So what I'm essentially doing here is adding 0 to the equation. But I'm adding 0 in a creative way so that we're able to go through the process. Okay, and then this will factor as x minus 3 quantity squared, and 34 minus 9 makes that plus 25. And so now we've completed the square, and how that helps us now is now we don't have both an x and an x squared variable. Instead, we have the quantity x minus 3 squared plus 25. Right? And you're only dealing with a linear x variable instead of both an x squared and the 6x that we were dealing with before. And that means that, hey, we can actually recognize this as a squared plus x squared. Right? We have a quantity, something squared, plus something else. Okay? And so that would make a be 5. And so what we do is we do the substitution here. x minus 3 gets replaced with a tangent theta. Right, and we can still differentiate. Dx equals 5 times the derivative of the tangent, which would be 5 secant squared theta d theta. Okay. And so now we're ready to carry our substitution process through. Dx is going to be 5 secant squared theta d theta, so that'll all go on top. On the bottom here, I'm going to have 5 tangent theta quantity squared. So in other words, 25 tangent squared theta plus 25. And of course, what I do then, what I end up doing here is I'll factor out the 25. Right, that'll give me 25 times tangent squared plus 1. But tangent squared plus 1 is going to become a secant squared. So carrying our substitution through, we'll do a little bit of housekeeping here. Since the 25's out and the 5's out from top, I can have that stuff factored out front. And I'm going to have secant squared theta d theta over secant squared theta. So the secant squareds cancel out, and we have 1 over 25, or 1 over 5, sorry, times the integral of d theta, which will just be 1/5 theta plus a constant. And then we go back here and say, well, okay, now we need to convert back to x in this case. So doing that, taking my x minus 3 equals 5 tangent theta, I can divide both sides by 5. So get that tangent theta is equal to x minus 3 over 5. So that means that theta is the inverse tangent or arctangent of x minus 3 over 5. And so here we had one that was an inverse tangent. You'll notice I didn't have to worry about, once I got it as a something squared plus a number, I didn't have to worry about the manipulations and stuff that I had to do before. All that stuff gets carried out in our substitutions. And so we end up getting the integral here. It results in 1/5 the inverse tangent of x minus 3 over 5.